Okay, I suggest we start. Okay.
Um,
You good? What do you think?
okay, yeah, we can start probably.
So our speaker today is Xin Fang, and we are very happy to welcome him at the seminar. Please.
Okay, so maybe I first share my screen. It will take a while.
So please, I also would like to say that we are recording the seminar. I hope you don't mind. Because there are some people who can't attend and who want to see the talk afterward.
Okay, so first I would like to thank the organizers for the invitation to give me this opportunity to give a talk in Moscow. I think it was last time, it was 2 years ago. We still have a face-to-face talk, and I really enjoyed that. Okay, so the topic I want to talk today is about Gröbner cones from quantum groups. Okay, so let me first say something about the outline of the talk. So essentially, my talk consists of 3 parts. So these are 3 different Gröbner theories. This first part, I will talk about non-commutative Gröbner theory of quantum groups. And then I will move to a second Gröbner theory, which is the Gröbner theory of constant partition or some root partitions. And the third part, I will talk about the Gröbner theory from the flag variety or the homogeneous coordinate ring of the flag variety, which is called tropical flag variety. And these 3 parts are connected together by one very special simplicial cone, which comes from either the Gröbner theory of quantum groups or from the Gröbner theory of this constant partition. And then I don't really assume that you know everything about Gröbner theory of all these cones. I will mainly do these things in an ad hoc way. So let's first start from this part, this non-commutative Gröbner theory of quantum groups. And the idea is from quantum groups, I will define some cone, and this cone will turn out to reappear in the constant partition and reappear again in this tropical flag variety. Okay, so first let me start with quantum groups. So this is the general setup. I want to first fix some notations. So I will take G to be a simple Lie algebra over the complex field, and this is usually of type A to G. And later I will restrict myself to some special simple Lie algebras. And let me denote throughout this talk N to be the rank of G. This is the dimension of the Gachdon. And I will denote W to be the wire group. And now the first thing I want to introduce, but I won't really define it because I don't really need definition of it, is the quantum group UQ of G. And here you see there's a Q. So Q is a generic parameter, which just means you can look at it as a variable. And my quantum group UQG is an algebra defined over C of Q, this rational function of one variable Q. And this quantum group is defined by, introduced by Drinfeld and Jimbo in the, I think 35, more or less 30 or 35 years ago. And they are deformations of the Euro universal enveloping algebra associated to G. But this procedure of associating a quantum group G to a Lie algebra G is not factorial, and this will cause quite some problem in defining and study this quantum groups, and it will also give us some new features of this algebra, which I will discuss later. Okay, so I will denote EI, FI, and KI to be the generators of the quantum group. So here I is between 1 and n. So they are the analog of the Chevalier generators as in the finite dimensional semi-simple Lie algebra. And now the quantum group has these generators. I want to denote the negative part of quantum group by this UQ of n minus. This is the subalgebra of UQG generated by this F, is F1 to Fn. And this is the free algebra quotient by this so-called quantum cell relations. So the quantum cell relations is you take the Euro cell relation in the Chevalier cell presentation of the Lie algebra, and you put some Q, some quantum parameter somewhere in a reasonable way. So you get something called quantum cell relations. And you see that this quantum group is defined with respect to this Chevalier cell presentation. So it uses the Chevalier generator. But if you want to really write down a basis, a linear basis of UQn minus using the Chevalier basis, this would be a quite hard question. So this involves quite something on this string parameterization or other things. So it's something definitely hard. So, but in the Euro enveloping algebra, if we look at the enveloping algebra of UG or U of n minus, there is a very nice basis arising from a basis of J. There is the PPW theorem. So the PPW theorem just says that you fix the total order on the, if you have a finite dimensional, for example, like in our case, a simply finite dimensional simple algebra, just fix the total order on a generator or a vector space generator of J, and you take the ordered product, you will get all the basis of the universal enveloping algebra. And now we want to see whether this kind of thing still holds for quantum groups for this UQn minus. Since they are generated by the quantum cell relation, and the natural idea is how to produce from this Chevalier generator something like a root vector. So this, but this is not an easy question because this UQG is not a factorial quantization. This procedure of quantization is not factorial on G. So it's really with respect to these generators. So the solution to this PPW theorem for quantum groups is solved by Lustig. There are some other works, earlier work, but this is completely solved by Lustig. So let me briefly recall how Lustig did. So how to get from the simple roots, the positive roots, there is a very standard way. So you fix the reduced decomposition. Let's take W0 to be the longest element in the wire group, and I fix the reduced decomposition called SI1 to SIN. Here, this SIK are the simple reflection, yes, these are the simple reflections. And now I can produce positive roots from this simple reflection in this way. So I take, for example, I fix some K, and then I act SI1 to SIK minus 1 on alpha IK, then this gives me a positive root. And then all positive roots can be obtained in such a way once the reduced decomposition is fixed. And this fixed reduced decomposition gives us an enumeration of the positive roots of G. This enumeration is just means the total order, which one first. So beta 1 first, beta 2, blah, blah. So for example, if we look at one very easy example, let's look at this reduced decomposition S2, S1, S2. And then I will start with alpha 2. This is beta 1. And our beta 2 will be alpha 1 plus alpha 2. And our beta 3 will be alpha 1. Because it's easy computation. Okay, now we have produced all these positive roots. And what Lustig idea is he defined something called the braid group operator Ti. So I will write here. Lustig defines some operator Ti, which goes from UQ of G to UQ of G. And then if you act Ti1 to Tik minus 1 on Fik, then he produced some element F beta k, and this F beta k is in UQ of n minus. This is an analog of the root vector as in the classical case. It really specialized to the root vector of that weight in the enveloping algebra. So he defined these quantum PPW root vectors. These are really in the negative part, although his braid group operator is on the entire part. So this vector depends on W0. So this quantum PPW root vector is really depends on W0. This is different to the classical universal enveloping algebra case. So, and he proved that if you write them in this order, beta 1 to beta n, as we have seen here, then this guy forms the linear basis of UQn minus. This is a quantum version of the PPW theorem. As you see, if you specialize this Q to 1, you will recover the Euro PPW theorem of UQn minus.
Do you want to explain the action of Ti?
I don't prepare to explain the action of Ti because this is given by some formula. It will act, maybe I don't really remember the formula. That's a problem.
Okay.
Yeah, it should act, I don't know. I think it will act on okay, how to say? If you look at the roots in UQ of J, it's just acts as the Euro wire group action. But the formula is quite long, so I don't prepare to say that. You can.
Is it a Hickey algebra action?
It's an algebra homomorphism. Yes.
Yes. Thank you.
Yeah, because Lustig essentially he defined four different Ti. So if you look at his book of quantum group, introduction to quantum group, he called Ti plus minus 1 or something. This is he defined different version of that. So, but they are equivalent. You can use any of them to find braid group action on the quantum group.
Yes, thank you.
Okay, so now at the position of this Lustig theorem of PPW theorem of UQn minus. Now we have a vector space basis of UQn minus, but UQn minus, it is an algebra. We want to study how to multiply two bases, let's say F beta I and F beta J. So if I is less than J, then there's no problem, we just multiply them. But if F beta J times F beta I, if I is less than J, then we have to write this guy, this monomial, into this form. So which means that we stratify this product into something which is called standard. This is a structure called an algebra with a straighting law. So you know a basis and you know how to write a non-standard thing to a standard thing. Standard thing just means these are in the basis. And now, if we look at the quantum group, we only need to look at what goes with F beta J, F beta I. We only need these two because the general you can be generated by these two. And this is the this structure is algebra structure with respect to this generator.
I'm sorry, Xin.
Yeah.
Could you perhaps turn off the microphone on the iPad? Because I think you have two microphones switched on, and I think this is leading to crackling. Everyone's getting the crackling sound, right?
Okay.
No?
I think I closed the iPad one because I didn't connect.
Well, here it says it's switched on.
Okay. Let me try to solve it.
But maybe it's
Page.
better to switch off the other microphone because we always have this noise when this micro is.
Yeah, that's what I mean. We have a crackling sound.
Okay, so maybe this is from the my clothes, and this is the microphone here. Let me try. Let me.
Well, maybe if you leave one microphone, it will be better.
Okay, so how should I do this? Okay, now
If it's difficult, then it's manageable. It's okay. Just a small background noise.
It's better now, or it's still?
Right now, it's good. It's good,
okay.
right?
Okay, I think the problem is this line here. I have the clothes, so it has it touches my clothes and.
Oh, okay, yeah, maybe that's it.
Yeah, maybe it would be better. I will keep this in mind. Maybe I put it in some better place.
Okay, great. Yeah, sorry.
Okay. I think now it should be better. Just let me know if it continues. I can just
No, it's actually. I think it's gone. It's much better now.
Okay. Yeah. Sorry for that. Okay. So this is the algebra structure with respect to this PBW generators of this quantum group. So the formula is given by this algebra with Streeting law structure is given by Lewendorski and Soybean, I think 30 years ago. The formula says the following. Here, if I fix K is less than L, then if I swap, if I multiply these two in the wrong way, then I have to stratify it to a correct way. So K less than L. And then there are something, first, there is some Q power appearing, and there is this term, this normal order term. And then there are some other terms appearing here. So this other term appearing has a very nice property, which means that these roots appearing here are really between K and L. So they are from K plus 1 to L minus 1. So they are really appearing in between. So this is a very nice property. So there's nothing before, nothing behind this L and K. And now here are some coefficients, and these coefficients are in Z Q inverse. And it depends on the power here. So you can forget about these brackets because these are some normalized divided power of this quantum PBW root vectors. So I don't want to go into detail here.
So okay. You already switched to SLN, right?
No, this is a general. This is for arbitrary J.
But what do you mean that the roots are in between?
In between, I mean here I give for fixed W0, I got enumeration of my positive roots.
Oh, enumeration, okay, yeah, right. Okay, thanks.
So yeah. So this just means I have a total order on them in between.
Yeah.
It's in between. It's not.
Okay. Yeah. Thank you.
You're welcome. Okay, this is the Lewendorski-Soybean formula, and this formula is very interesting. We encountered this problem because the first idea was we want to generalize the PBW filtration to the quantum groups, and now the first question is if in the classical Lie case, if you take the PBW degree 1, give this degree 1 to every root vector, then you get a filtration. But this is not true in the quantum group case because this part, it could be annoying. This part is of degree 2, but here there are examples, for example, in G2 saying that it may have degree 3. So you won't always have PBW filtration if you give everything to degree 1. So that's this Lewendorski-Soybean formula. And now we want to study this Lewendorski-Soybean formula better. The reason is if you study quantum group and representation theory, usually people uses the simple roots, the Chevalier presentation. And now if one want to use the PBW, quantum PBW root vector, then one has to use this kind of relation, not the quantum cell relation. So this is quite different. And now if we want to use some relation, the first question is, what are these relations? So to understand this relation, the key point is what is this coefficient here? So I think it's already 30 years and there is no general results about these coefficients, except that in some cases, this guy is divided by 1 minus q. This from specialization. So, but in general, there's no such result.
So when the roots are simple, can you say something?
When these roots are simple, then you see here, if these two simple can be glued together to a positive roots, then these positive roots must appear here. The reason is the quantum group negative part, let's say this uq of n minus, it can be specialized with q go to 1 to
Well, wait, when the roots are simple,
minus.
that's the quantum cell relation, right?
Yeah, that's quantum cell
okay,
relation.
okay. So, yes.
And from specialization, you know that if you have two simple roots and the sum is a positive root, then this root must appear here.
Yes.
Because from this way, the total order you get from this way is a convex ordering. So this means this also, there's no contradiction here.
Okay.
So the main question here is how to understand, how to get these coefficients. So this is the question. What do we know about these coefficients? And if, for example, this is such a hard question, there is no good answer. Up to my knowledge, there's no answer in the last 30 years. So we move to understand an easier question, which means that when this coefficient is non-zero, it's way easier, but still, we can't completely solve it. But we use some, our approach to understand this question is motivated by the algebra with Streeting law. So once you have this algebra, so Peter, you have a question?
Yeah, I just got confused by this comment that when you have two simple roots, I think these are not the quantum cell relations, because the quantum cell relations, there you only have simple roots. But here you will get, when you have two roots which are neighbor to each other, and these relations here, I'm sure you will also have the roots which corresponds to the sum.
Yeah. Yes. So yes. So if you have f alpha I and let's say f alpha j, if you have minus q alpha I alpha j f alpha j f alpha I, here you may have f alpha I plus alpha j appearing here. And there's some coefficient here. That's what I wanted to say. Yeah. Yeah, and yeah, I think this has some relation to the quantum cell relation, but not completely.
No, yes, I meant that you have the relation, and then you apply. You have to still decompose it with respect to the basis.
Okay. So let me read this guy, and now let's have a different point of, have a slightly different view to this question. So I want to make use of this algebra with Streeting law structure. And then in the Gröbner theory commutative case, then if this algebra with Streeting law usually comes from the reduced Gröbner basis of an ideal. Here, I just give you some idea from the commutative Gröbner theory, where I is an ideal in a polynomial ring and I have a monomial ordering. So in this case, we can produce something called reduced Gröbner basis associated to this ideal I and this monomial ordering. And this will play the role of the algebra with Streeting law structure on the quotient ring. And from this Streeting law, we can produce some Gröbner cone. And I will not explain this in general, but I will do in this case in the ad hoc way. What is ad hoc way is the following definition. So this definition is due to the joint work with Theo Backhaus and Ghislain Fourier in 2017. We called it quantum degree cone. So what is quantum degree cone? That's this is the formal definition. I think I will explain it. I think it's better to explain it in this Lewendorski Soybean formula. What does this mean? It means that this cone consists of some degree function, which means that I gave all this guy some degree. So this guy get a degree d beta L, d beta plus d beta K, because I want to give degree d beta to a quantum PBW root vector f beta. And then this guy will get a degree d beta K plus 1, and I have to multiply it with nk plus 1 plus here is nl minus 1 d beta L minus 1. And now this quantum degree cone, just the only condition we need here is I want this guy, because this one has the same degree as this one. They have the same degree. I want this degree is larger or equal to this degree here, which just means I want to keep this Lie bracket. This is the usual thing in the PBW filtration.
So you mean you want this inequality to be true for each non-zero C, right?
C, yeah, for this is what I want to see next. Yeah, thanks. I have to, I need that this C is non-zero. So this is the thing in the definition I write here. So this quantum degree cone consists.
I'm sorry. What is degree? Is it like a number or
it's a number? It's a number. It's a real number.
Yeah. And what is the cone then? If degree is a number.
Sorry?
Okay.
Maybe
you will explain it.
Yeah.
So the cone sits inside the real vector space, and the coordinates in this real vector space are these numbers d. So you have inequalities for these d's, and this is exactly the definition of the cone.
So maybe if I look, I will finish this definition and then I will move to example. That might be clearer. Okay, so this cone consists of those degree function. Degree just means for each element for each positive roots, I can identify the positive roots with the quantum PBW root vector. And then for each of them, I give it a degree. And then I want that if this coefficient is non-zero, then this degree of the left-hand side of this beta K, beta L term is larger or equal to the right-hand side term. This is what I want to say for this definition. And let's look at one example, then the things gets easier. So let's look at this A2 example. So W0 is now S2, S1, S2. And this then we know that beta 1 is alpha 2, beta 2 is alpha 1 plus alpha 2, beta 3 is alpha 1. And now in the quantum group, there's only one Lewendorski Soybean. There's only one relation as a splitting law. It's this one. And from this one, we know that this gets degree d beta 1, this gets d beta 1 plus d beta 3, and I want it to be larger or equal to d beta 2. The idea is I want to simplify this quantum group by assigning the degrees. And this is the cone. There's only one condition. There's only one inequality to define the cone. For example, in this case, if you give everything degree 1, if you give this degree 1, then it's of course satisfied. So the first fact, the first thing if you have such a cone is you want to know whether this cone is empty or not, whether it has only trivial elements. So the first fact is that this cone is non-zero, and it is a polyhedral cone of dimension n. So this n, I just mean recall that this n is just the cardinality of the positive roots, because this cone is full. Just mean that this cone is full dimension. Now I have a cone. It describes how to degenerate a quantum group, and I want to know what are the facet description. The hard point is that this guy, we don't know whether these are non-zero or not. So to get a facet description looks not that easy. Okay, so to get facet description, I want to introduce one new polyhedral structure, which is called the Lustig tight monomial cone. So then I will identify or this dw0q of J, this quantum degree cone, with the Lustig tight monomial cone. So this Lustig tight monomial cone appears in the study of monomials in canonical basis. And it also appears in many different places, for example, in the cluster theory and in the different algebraic combinatorics. So I will fix my reduced decomposition W0. And I need to introduce one more condition or notation. Is if I have a P, which is between 1 and n, I will denote P bracket 1 to be the next place where the IP appears. So this is the definition, but I think it would be easier to understand it if you look at this following example. So in this example, I will 3 to S3, S2, S3, S1, S2, S3. So I start from here, S3, and here P is 1, and S3 appears also here. So P1 is 3. It's just a position where IP appears next time. If IP does not appear, then I will give the 0. So then I continue this example. If I have S2 here, it appears at position 5. So 2 of 1 is 5. And this 3, I look at S3, it appears as 6. So this 6. And S1 here does not appear. So it's 0, 0, and 0. This is just definition of P. And from here, I define a polyhedral object, which is called the Lustig tight monomial cone, LW0 minus of J. This minus here just stand for this part where I have a larger or equal. If you have smaller or equal, I can write a plus here. It doesn't. Here I use the minus. So LW0 of minus of J consists of those xi in Rn. I will give coordinates to Rn as x1 to xn, such that xp plus xp of p bracket 1 plus every inner product of the positive roots in between is larger or equal to 0 for all p1 non-zero. So this definition is here. I think if you look at the example, then it's easier always. So for example, if I look at this A3 example, then the first inequality is P is 1. So I get x1 plus x3 minus x2 is larger or equal to 0, because S3 bracket alpha 3 bracket alpha 2, I get minus 1. So then I have x2 plus x5 minus x3 minus x4 larger to 0, and then I have x3 plus x6 minus x5 larger.
Sorry, excuse me.
Yeah.
Is there an XS missing in the definition?
Yes.
Ah, okay.
There
Thank
is
you.
a,
Yes, thank you.
otherwise
Bea.
it's not, the origin is not 0.
XS, sorry. Yeah, thanks, Bea. Yeah, this XS missing. Peter, you have a question? No. So this is the cone. You see that this is the 6-dimension cone in R6. And if you have a closer look at it, it is have 3-dimensional linearity space, and it is a simplicial cone. But I will go back to this later. Now I want to identify this quantum degree cone with this Lustig tight monomial cone. But the first thing I need to look is this cone are unfortunately in different space. One is in R delta plus, the other is in Rn. I need to identify it. I just use this enumeration of positive roots to identify them. So now they are in the same space. I just identified d beta I with xi. Now they're in the same space, and I can state the theorem. Okay. The theorem says this is the joint work with Christian Fourier and Markus Heineck. The paper is in press, and I think it will appear this year in the journal. And so the first result says that the quantum degree cone is always contained in the Lustig tight monomial cone. But there's one thing which is I have to use the long length dual of the Lie algebra for the Lustig tight monomial cone. This long length dual is usually it's not something I think it appears in many different places when you want to parameterize the canonical basis. So like in the work of Bettelstein and Lewendorski, people always need to go to the dual Lie algebra, to the long length dual for the parameterization. And this is always contained. Now there's in one very special situation when J is simply laced and W0, this reduced decomposition is compatible with the orientation of a quiver. But I don't really want to explain what that means, but this just means that for some very nice W0, we can prove that these two cones are the same. So which just means that we know all the facets of the quantum degree cone. We know all of them because this part, we know the facets, but these are defined by the facets. And we conjecture that for any simple Lie algebra, these two are the same. But we have no idea at this moment how to prove this conjecture.
So you don't have an example where they're different, right?
No. I think I computed quite some example in the case C4. It's big enough, but they are always the same. But it's not always easy to see, but they are always the same.
I see.
Will you say what the facets are for the Lustig cone?
These are the facets. So
okay, this is a minimal description.
Yeah, because these are the facets because they have different XP.
Okay, I see.
Yeah, for example, here you can look X1, X2, and X3, and all other things are larger than this guy, the indices. So you have a simplicial cone in this case.
It's simplicial, right?
It's simplicial up to a linearity space.
Obviously, yes. Okay, but will you expand on the algebraic meaning of this cone you defined? Because
yes, I will. This is the next thing.
Okay, great.
Yeah, this is degeneration.
Well, yeah, that's the question whether it's actually a degeneration.
Yeah. Okay, so now let me move to this is the theorem. I don't think I want to explain the proof. The proof of one is quite dirty because we have to use quite complicated computation in quantum group to estimate some coefficients are non-zero. It's a long computation. And the second proof uses because we are looking at quivers, so essentially we are using the Alexander-Rayton theory or the Serre duality there. But anyway, what's important for this talk is that we want to use this to study degenerations. Okay, good. Now let's answer Igor's question. Why we study this cone? First, I write this formula here to just remind you these properties. So first, for any element in this quantum degree cone, I think here I should this the typo. This is d beta I. Yeah. So if I give the d beta I to be, if I give the quantum PBW root vector f beta I degree d beta I, then this induces a filtration on UQN minus. This is clear from this algebra structure. And now if I take the associated gradient, then I get a degeneration of the quantum group, negative part. And second property is that this second property looks like in the classical Gröbner case. So this associated gradient algebra does not really depends on on D, but it depends on which phase D, which open phase D lives in. So it's the second part. This guy depends only on the phase lattice of the quantum degree cone. And now, from what we have proved above, if we look at the quiver compatible case.
Xin, I'm sorry.
Yeah.
What do you mean by phase lattice?
Phase lattice just mean this is the polyhedral cone.
Yes.
So I have the phases, and
Yes.
now I can define a partial a poset structure on these phases by inclusion.
Okay.
And this turns out to be a lattice.
Ah, okay. Okay. I see.
And this is called phase lattice.
Okay.
And the quiver compatible case, the nice thing is we know this cone. This cone is first, it has an n-dimensional, small n-dimensional linearity space. This, if you look at this, this linearity space is exactly given by the zeros. Zeros here. This is a linearity space because there's no condition on when P1 is 0. So it has an n-dimensional linearity space, and then I can quotient this space out. Then I get a simplicial pointed cone of dimension n, big N minus small n. Now, what the simplicial cone looks like, it just means that at the apex, I have something looks like a simplex. And this means that the phase lattice of this cone is a Boolean lattice. Boolean lattice is, how to explain? It's a lattice of something like this. Okay, this is a power set of the n minus n. With the set inclusion, this is a Boolean lattice. And this Boolean lattice implies a degeneration poset of the negative part of quantum group. Because of this part 1 and 2, we get a degeneration poset. So the degeneration poset of the UQN minus, which with respect to the PBW basis, is a Boolean lattice. Now I want to explain all this in the following example. As always, to have more examples. So in this example, let's take our favorite reduced decomposition 3, 2, 3, 1, 2, 3. And in this case, what I have shown you that this is the DW0 Q of G, this quantum degree cone. I just translate between two parts. One is R big N, the other is R of delta plus. I just translate into these two coordinates. This is the coordinates here. So I get these three inequalities. So I think Evgeny and Igor should be very familiar with these inequalities. And now, if I will explain later how this relates to what we did. And now, if I look at this phase lattice of this quantum degree cone, it looks like this. You see, this is a cube. It's a Boolean lattice of 3 elements. And here, when I write A, B, C, I mean A takes equality, B takes equality, and C takes equality. All of them takes equality. This is just this ABC, and the empty set just means none of them take equality. All of them are strict. And this is the phase lattice. And then we get, from what we have seen above, we get the degeneration poset of the quantum group, UQN minus. And here, if I take something from the empty, which just means all the inequalities are strict, then I will get the skew symmetric algebra as the associated gradient. If you see this equation here, this is clear because I kill this part. If I kill this part, you will get a skew symmetric algebra because you have beta.
Yeah, is it really skew symmetric or some powers of Q appear?
Yeah, this Q appear here.
Q symmetric algebra.
Yeah, it's skew. Okay. I say
not skew symmetric.
Okay.
Q symmetric.
Yeah.
Yeah, that's the quantum group notation. Usually people call the skew symmetric because there is the derivation or automorphism appearing. Yeah. So it's Q symmetric. Yeah.
But sort of in for this decomposition, for general Slan, do we know any of the intermediate algebras?
Okay, so Igor, you're always predicting the next part of the talk.
Okay.
So now I want again to answer your question. What are these things here? What are these question marks? What are these algebras in between UQN minus and SQN minus? So if the point of view I want to give is via slightly different. So why these UQN minus are important? Because it has some canonical basis, and these canonical bases are very nice, which have very nice properties. And how this canonical basis, how Lewendorski comes out with this canonical basis is he is motivated by the work of Ringo. And Ringo gives something like the categorification of the quantum group via representation of quivers. And then Lewendorski used the geometric version to interpret this counting number as some sheaf counting, or to generalize this to a geometric setup and to define this canonical basis. And now I want to do the similar thing. I want to understand these algebras using quiver representations. This next part. So how this goes. So now I want to go to a slightly different level. I want to go to the categorical level. So let's assume that in this case that G is simply laced, and it is, which is ADE case. And I assume that Q is the quiver with underlying graph is the Dinkin diagram of G. So, and now we have this mod KQ is the finite dimensional modules of the path algebra of the quiver. And K, I will later say this is just FQ. I can take a finite field. So what Ringo proved is that the negative of the quantum group can be realized as a Hall algebra, as this isomorphism as the Hall algebra of this category mod FQQ. And I want to give you a crash course on the Hall algebra. What does this mean? The Hall algebra means that for a nice category, the Hall algebra has a isomorphism class of object in this category as vector space basis. And this is a vector space basis, and now we want to multiply the spaces. How do we multiply? The multiplication is controlled by how these two objects, how one can extend one object to with the other. This is extension one of these two objects. So this is just the Hall algebra just characterizes or it's an algebra whose multiplication encodes the extension structure of the category. So if this is the idea of Hall algebra. So Ringo showed that this negative part is the Hall algebra. And now the question is, how can we categorize this associated graded stuff using Hall algebras? And the answer is the following. So if we look at the Lewendorski-Soybean formula, it is quite similar to this one, because it has a basis, and we multiply 2, we get something on the right-hand side. So degenerating the multiplication in the negative part of a quantum group is the same as we want to kill some extension between two modules over the path algebra of a quiver. And how to kill extension, but extension are there, so we can't really kill them. But the idea is to study some structure which allows us to kill the extension. We don't look at abelian structure of the quiver representation category, but we look only at the additive structure. And we look at these extensions as an extra structure on the additive category. So this is something called exact category. This exact categories, I will use the version of Quillen. This are, roughly speaking, these are extension closed categories associated to an abelian category. So I won't really define them, but I just want to use this very intuitive way to give you some intuition. An exact category is an additive category, and I designate some of these three-term sequences to be exact. So, and now if you look at this definition of the multiplication in the Hall algebra, you see that what one really uses is this extension structure. And it is in fact a theorem proved by Ringo and Hilbery. And essentially it's proved by Ringo and it's written down in the setup by Hilbery. So it means that having an exact category is enough to define a Hall algebra. So,
Xin, I'm sorry, may I ask a clarifying question?
Yes.
So, well, you are saying that we have to specify what sequences are exact, right?
Mm-hmm. Yes.
But it seems that in the abelian category, the exact sequences are already given. So they are kind of.
So here I only have an additive category. I forget the abelian structure.
So you're not defining kernels and co-kernels,
No,
but
we designate, we choose which arrows are kernel, which arrows are co-kernel.
Okay, thank you.
Yeah. And this is here, which sequences are exact. And sequence just means three-term sequences are exact. So, okay, so why we are interested in this? Because this one, we can get, okay, I have to say, this is the consequence of a result by Enomoto. He proved that for nice additive categories, I don't want to say how nice they are because these are some maybe abstract nonsense. For example, the example I have in mind is mod KQ. This is a equirepresentation category. They are nice. So the exact structures, they form a Boolean lattice. And now we can really use the exact Hall algebra of exact category to give a description of this degeneration of the quantum group. So this is a joint work with Lewendorski, and I assume that we are in this compatible case.
I'm sorry, may I ask one more question?
Yes.
So can you give a hint how an element from the Boolean lattice allows you to define these short exact sequences, at least few words, I don't know, if possible?
Okay, so this Boolean lattice is how to say, this goes via the Auslander-Ryton sequences, almost split sequences. So I take, for example, I take a type A3 quiver. So the Auslander-Ryton quiver is of this form. So there are three Auslander-Ryton transforms. So one goes here, one goes here, and one goes here. And these are the three prototypes I want to take. And then I take the Boolean lattice over the three.
Okay.
And they will generate if I choose any subset of the three, they will generate exact structure. This is
in particular, you are saying that the size of this Boolean lattice is 2 to the number of these AR transforms, right?
Yes, it's exactly n minus n.
Okay, I see.
Because you have the projectives on one side, there's nothing there.
Right.
These are the n, which are the projectives.
Okay,
so if you look at this, this is the 4-term relation, this is a 3-term relation, and this is a 3-term relation. So these are exactly what we get previously in this example 3 to 3, 1 to 3. Because here you take 3 to 1, and then you can see that this is 2, 3. Here you have 1, 2, and have 1, 2, 3. So these are exactly these relations. It's this is exactly what this theorem says in a precise way. But here I didn't want to introduce this Auslander-Ryton transform, so I just state it in a not that precise way.
No, it's okay.
So the theorem says the following: for any exact structure on the equirepresentation category, there exists a phase, a unique phase of the quantum degree cone, such that algebra of this category isomorphic to the associated graded algebra of the negative of the quantum group with respect to this phase. Because for each phase exists a degeneration. You take the interior of the phase, you take any element in the interior as the grading, and you take a filtration and associated graded. And this is the first part. And second part says that all this degeneration arise in this way. And the third part says if one exact structure is smaller, this is just a set theoretical containment in the other, then this larger one is the phase of the smaller one. This result is, this is the mathematical way of saying this, but in an intuitive way, it says just the following. We have the lattice of exact structures where the lattice structure or the process structure comes from this inclusion. And then the other side, we have the phases of the quantum degree cone. These two lattices are isomorphic, and they are both isomorphic to the degeneration of the negative part of the quantum group.
But so the inclusion of these exact structures, this means that you have more exact sequences, right?
Yeah, you have more
inclusion of the sets of exact sequences.
Yes. You could,
okay.
Yes, exactly. So this is exactly the set theoretical inclusion. And here I have to turn it around. I have more exact structure, then the phase becomes smaller. So this is the, I think this answers Igor's question. How can we describe this degenerated?
Yeah, well, I meant if there's, actually, I was hoping for something like more direct, if some of these algebras or some, like, well, this is, of course, a description, but are there other, for maybe in some special, one special case or something, is there like some more down-to-earth description of the algebra?
You see, the problem is that this quantum group associated to Lie algebra to the quantum group is not factorial. So although you can study some Lie algebra arising from these phases, but the, you can't quantize it. So this degeneration is not that compatible with the Chevalier generator. So,
yeah.
But if you, I don't have a precise description except this exact structure way. The problem is we don't know what this coefficient. So if I go back a bit, where this is, we don't know too much about this coefficients here.
Okay, but can I ask a more precise question? So
yes.
In the case of this compatible decomposition, this is how you describe all of the algebras in the corresponding to all of the faces of the cone, right? Question: so if the decomposition is not compatible, right? So it's one of the not so good decompositions. Will the set of appearing degenerate algebras, will it be different up to isomorphism? So can you have essentially new algebras appearing, or might they actually be isomorphic to this case?
If it's
what was that clear?
Okay, so you mean is there any new because this degeneration is really depends on W0.
Yes, that's why I'm asking. So
so if you have if you have a non-compatible, then you definitely have more have new degenerations.
You've checked that you actually have new algebras up to isomorphism.
I don't know whether they are up to isomorphism, because this is hard to check.
Well, yeah, it is.
Yeah, but this Streeting law are different. I think we have different Streeting law, but I don't know whether they are different up to isomorphism.
And if you take two different but compatible decompositions, the straightening laws will also be different, right? But the algebras will be the same up to isomorphism.
Here, the degeneration poset of UQN minors does not mean that this is up to isomorphism. It's just the degenerations. One, you can degeneration further, then you have this smaller. This is just a poset. I'm not saying that this is up to isomorphism. I'm not saying that you have two incomparable post elements in the poset, they are just not isomorphism. No.
No. It's not. I meant. Well, maybe I can ask you afterwards. I meant different. So you take two different W zeros. I was trying to compare that.
Yeah, this I have no idea because really to prove that these two things are not isomorphic, it's really hard because these are non-commutative algebras.
But your theorem with Misha says that actually they will. So the algebras you obtain, they will be the same for different W zeros as long as they're compatible with the quiver.
No, we're not saying these are the same.
Wait, so this...
No. We don't say this. We don't compare different W0. We only fix W0.
Because Igor, you see, for different W zeros, those betas are going to be very different.
Yeah.
So it's
yes. But if we look at this whole algebra, this H of E, right?
Yeah.
How does this depend on a decomposition or whatever? It doesn't, right? So this ingredient in the theorem, that's what I'm saying. This ingredient.
No, the E,
whole algebra.
The E depends on Q. Q has an orientation.
Okay, E depends on Q.
And Q has an orientation.
And the orientation of Q depends on W0.
Yeah.
Right? Oh, okay. Yeah, then this makes sense, right?
Yeah.
Okay. Thanks.
May I ask one more, much more down-to-earth question? So let us consider the extreme case of SQ. Okay.
Yes.
So then, do you understand correctly? Then you want to avoid any exact sequences in this case, or not?
Yeah, only the split one. There's only split one. Only split sequences are exact.
Okay, but then, so how are you getting this term Q to the scalar product of beta 1, beta 2?
Beta 1, beta 2, there's no, but there's one on beta 1, beta 3. F beta 3, F beta 1 is Q minus 1 times F beta 1, F beta 3.
But didn't you have their scalar product of two betas?
Yes, this is minus 1 here.
It's always minus 1 or what?
No, this is a beta. This is I confused. So this is a beta 3, beta 1 in general.
So this is an example or what?
Yeah, this is example.
But in general, you have something here, right?
Yeah, in general, we have F just, this is just if I write beta J, beta I, this is beta J, beta I, and beta I, beta J. It's just this.
Right.
This is the,
then I'm just trying to compare with your definition of the whole algebra. So
yes, yeah. Okay, I see. So the thing is, you see here, the thing is, I only define this as x times y, and then you have to look at uy times ux.
Yes.
And then you take the q. Okay, maybe I write here. You have uy times ux, then ux times uy, and these two are the same up to q some power. These are the same because there's no extension.
Right, but then the question is, why does this power show up? So,
Because of this extension 1, there's a 0 inside. This is comes from the trivial extension.
Oh.
And from this formula, which one is the quotient, which one is the sum?
Okay, thank you very much.
Okay, so now let's go to one special cone. So this is our favorite case where Q is just a line, it's equi-oriented. And the compatible reduced decomposition is just this one. So I think you're all familiar with this one. It's very nice. So
It's
and
the
then
only compatible decomposition.
no, you can have other, but I choose this one. Yeah.
Okay.
You can do 2 moves, something like that. But I choose this one. Yeah. Okay, and then this dW0 of Q, or quantum degree cone, is given by exactly this kind of inequalities. And what are these inequalities? I think you don't really need to read it. I think I will draw a picture and then you understand it. So the point is this degree plus, okay, I have to maybe write more. Here is alpha 1, alpha 2, alpha 3, this is 2, 3, this is 1, 2, and this is 1, 2, 3, alpha 1, 2, 3. Okay. And now this degree plus this one is larger equal to this one. This degree plus this degree is larger equal to this one. And then the degree of this one plus degree of this one is larger equal to degree of this one plus degree of this one. So this is exactly the facets of this cone. Okay, this is just one example. And now I want, in the next part of the talk, I want to mainly give a different point of view of this cone, and then move to the tropical case. So let's go to the next one. So the next one, I want to recover this cone as root partition or constant partition cones. So how this goes? Again, I need to fix some notations. So let J be a reductive group, and with Lie algebra, the J as before. And I fix my and then I have the U minus. This is the opposite unipotent. And for beta, a positive root, I will take a generator of the Lie algebra J of weight minus beta. This space is 1-dimensional. I take a non-zero generator. And then I have the corresponding root subgroup. Now, this is the key point here is definition. I think that was the topic of my talk 2 years ago. This is called a birational sequence introduced in a joint work with Jason Fourier and Peter Litterman. And this, I have the definition is the following. I have some positive roots. There are exactly n positive roots. And I recall you that n is the cardinality of the positive roots. And this set or this tuple of positive roots, there might be repetition, I don't care. It's called a birational sequence if the following multiplication map, this multiplication map goes from the product of all these root subgroups to the opposite unipotent. And I will just give you this very explicit formula. This map is birational. So for example, if I look at the example I had before, if I fix the reduced decomposition Si1 to Sin, then this alpha I1, alpha In, this alpha I, these are the simple roots. This is a birational sequence. And furthermore, if I look at this beta k I just defined as above, then this one is beta 1 to beta k is also birational sequence. In this case, it's even isomorphism, this map. It's isomorphism. Okay, now I assume that I have a birational sequence. I want to study some Gröbner theory associated to this birational sequence. So if you want to have something in mind, you take this easiest example, alpha 2, alpha 1, 2, and alpha 1. This is if you have this example in mind, then everything becomes quite easy. So I will define a Gröbner cone from this sequence. How to define it? So here, if I have this gamma k, I can write this gamma k as the sum of simple roots. And here are these coefficients. Or you can write this is just the gamma k inner product with the fundamental weight. So then I have this formula. It's how we do the partition of gamma k into simple roots. And now I want to write this one in a polynomial way, which just more or less we take the exponential of it. How does this mean? I consider a polynomial map. It goes from q x1 to xn. This n is the same as this n. So here, this xi or sk, you should have in mind is this root gamma k. And now I map it to t1 to t small n. And it's just I map gamma k to how it decomposes into simple roots. And then this I write it in an exponential form. It's just t1 ak1 to tn akn. If you look at this easy example, so this map phi of s looks like x1 to t2, because this is alpha 2, and x2 to t1 t2, and x3 to t1. And that is exactly this polynomial map. And now I take is to be the kernel of this monomial map. So it's kernel of phi.
So far, this is independent of any birational sequence, right?
No, it's now. I just assume that S is birational.
Okay,
It's arbitrary. Yeah, it's arbitrary.
Okay.
And in this example, this kernel is clearly it's just x1 times x3 minus x2. So what is the combinatorics behind this? It's just a constant partition. I want to see how to write a root into different way. For example, these are two different way of write roots alpha 1 plus alpha 2. So this ideal tells you how to move from one root to the other, from one partition to the other. And now I fix. I will start doing Gröbner theory. Really, Gröbner theory now. I fix the monomial ordering on my polynomial ring here. For example,
may I ask a question? So if all the roots were simple, I mean, all the gammas were simple, then the ideal would be just some coordinates are equal, right?
Yeah, just some coordinates are equal. Yes, these are exactly. These are just some. Yeah.
Thank you.
So now I look at this monomial ordering on this ring because I want to do Gröbner theory. I need a monomial ordering, and then I have something called the reduced Gröbner basis. What is this? This is a very nice generating set of this ideal IS with respect to this ordering. It's just a nice generating set. And it's always in this setup, it's always of form xai minus xbi. And here, this xai, this ai is, this monomial is larger than this monomial with respect to this monomial ordering. And then from this reduced Gröbner basis, I can define a cone. And this cone is just those weight vectors. So I want W here is in Rn, just mean that W give each of these generators x1 to xn some degree. And I want this degree to preserve this monomial ordering. It's just a degree which do the same thing as monomial ordering to pick out monomials. For example, this is a polyhedral cone. This is an open cone. For example, if I look at...
I'm sorry, this initial monomial order, you think, is it an arbitrary one or you need some conditions on it?
No, it's, at this moment, to define it, I only need a monomial ordering.
Okay, thank you.
I just need to compare these two, that's all. So, and this cone just mean I compare, this comparison is the same as this comparison. I can use either the monomial ordering or this weight vector W to pick out terms. So this is the idea of this Gröbner cone. Just to, because the monomial ordering is too complicated, but the vectors are easier. So for example, if I take, in this example here, IS is this guy. I take the lexicographic ordering, then this x1, x3 is larger than x2, which means that if I want to use some vector to pick out w x1, x3, I want to other than x2, then the only condition I need is w1 plus 3 is larger than w2. So it's just such a cone. Now here's a theorem. Let's go to some special case. Let's assume that J is simply laced and W0 is compatible with the quiver. And I take the special birational sequence S W0 to be beta 1 to beta n. So this beta I is as before. This beta I is SI1, beta K is SI1, SIK minus 1 of alpha IK. This as before. Then this cone coincides with the loose-tick tight monomial cone, and it coincides with the quantum degree cone. So the same cone appears in another setup with the root partitions. So this is the theorem. So two different Gröbner theory. One is non-commutative quantum group. The other is commutative root partition. Finally, these are the same.
And so, can I ask a question?
Yes, sure.
So here, this ideal, I guess it's a toric ideal for this set of points, for these coordinates, right?
Yes.
And so it is, the set of points is always convex, right? It's the set of vertices of a convex polytope, right? I mean, what can you say about these polytopes? So for each birational sequence, you obtain a polytope of dimension.
I can't say for each birational sequence, but I can only say for this particular birational sequence. Because, for example, you take alpha 1, alpha 2, alpha 1, then you have repetitions.
Yes, you have repetitions, but I mean, you can consider they're convex. How? In some case, can you say something about these polytopes? I mean, in this not compatible case or any other case. I mean, it's a small dimensional polytope, right? It only has dimension n.
Okay. No, I haven't thought about this question. No. It will introduce a subdivision or something like that. But I haven't thought about this question. I don't have immediate.
No, I'm just trying to wrap my, if this ideal IS, if it has some like geometrical, so it defines a toric variety. Can we say it's a toric ideal, it defines a toric variety. Can we say something about this toric variety?
No, I haven't thought about that.
Okay, but it is a toric ideal, right? And
yeah, it's a toric ideal. Yes.
You have it written down there.
Yeah, it's a toric ideal. This is, you can associate to any vector partition problem, this toric ideal.
Yeah. Okay, thanks.
May I expand a bit on Igor's question? So
yes.
you started with the sequence of gammas, right?
Yes.
You attach to the sequence toric ideal or a toric variety, and this correspondence works independent on whether your sequence is birational or not, right?
Yes.
Now the question is there some special feature of these ideals or of these varieties while coming from the property that the initial sequence was birational? So, I mean, is there something special with starting from birational sequence? So can you somehow, because actually, so there is a problem of characterizing those birational sequences, and I wonder if this construction does give you some way to check or at least to understand something.
Yes, this is a very good question. I think it's, I don't have immediate answer at this moment, but I think it's worth studying this question. Yes, you're right. This root partition, yes, I think, yes. Yeah, I think I don't have immediate answer, but this is really a good question. This should relate to the constant partition.
Mm-hmm.
Whether we, at some degree, we get, at some weight, we get enough constant partition.
Mm-hmm.
Sorry, right.
Yes.
So there you gave the two basic examples of birational sequences, right?
Mm-hmm.
One with simple roots and one with all the roots.
Mm-hmm.
So in the second example, where you have every positive root once,
Mm-hmm.
there you have the same IS independent of W0, right? In this second example. Could you show the example maybe again?
You mean this example here?
Yes, example 2. So
It depends on W0.
no, the sequence depends on W0. I'm asking whether IS doesn't depend on W0, right? Because I mean
no, IS depends on W0 because this is the sequence. This phi S is closely related to the sequence. If IS does not depend on W0, then this theorem is just empty because all these cones should be the same finally.
Wait, could you show me? Could you go up a little bit?
Yes.
So you're saying.
So this is just vector partition. How you write a vector into, how you write a weight or a root in the root lattice into positive roots.
But Xin, am I right that the order of gammas does not really play?
Yeah, that's what I'm saying. That we have the same gammas in different orders.
They do because we fix this ordering.
Yeah, but I mean, if
no, but I mean the ideal IS. You're talking about initial ideals of IS. I'm talking about specifically the ideal IS does not.
Okay, you mean the entire ideal?
Yeah.
Ideal IS.
Yes. Okay, ideal. This should up to permuting this the same ideal. Yes.
Yes, that's what I'm saying.
You're right. Yeah. Okay. Yeah. Up to permuting the sequences of here, this is the same idea essentially.
Okay.
Yes. Thanks. No. This is the same cone appearing in two different places, and now I want to go to the last part of the talk. I think I will go quite quickly. This is how to use these cones from the first two parts to look at the tropical flag varieties and to give our joint work some different interpretation. So in this case, I will go back to the third Gröbner theory. And this is the, let me first explain the setup. So I will concentrate on the case where J is of type AN and a very particular birational sequence as a previous example. This is compatible with the reduced decomposition n minus 1 n and blah blah 1 to n. This reduced decomposition. It's compatible with the quiver, this linearly ordered quiver. This is this sequence. And now I will denote this Cn plus 1 to be this cone, Gröbner cone arising from vector partition or root partition or from the quantum group. But the important thing is this cone has this kind of inequality. And now I will briefly recall you the tropical flag variety, just a very quick thing. So the flag variety, I will denote flag n plus 1 to be the Euro flag variety. This is the nest of a net of subspaces in Cn plus 1. And I will denote, I will look the flag variety using the Pricker embedding. I will consider only the Pricker embedding into Grassmannians and then into this product of projective spaces. And now I will denote PLN+1 to be the Pricker ideal. As it's a defining ideal of flag variety in this multi-projective spaces, and it is an ideal in this algebra in this polynomial ring C of Pi, where this I is IN+1. This is the notation for all possible Pricker indices. It's just the union of from n+1 element you choose k elements to 1 to n. This is just a Euro notation. And what is the tropical flag variety? This means this tropical flag variety consists of those weight vectors. I give all these Pricker coordinates a degree. This is here, a degree of a Pricker, such that the associated initial ideal contains no monomial with respect to this degree, W. And I want a normalization. I want W of 1 to k. What does this mean? This means the degree of the Pricker coordinates P 1 to k. This degree is 0. This is quite natural normalization for all k between 1 and n. From the famous Bieri-Groves theorem, we know that this tropical flag variety it is a pure polyhedral fan of dimension big N. This big N is the number of positive roots in the type A. And so it's a polyhedral fan. So it's a natural question to understand or to describe what are the cones in this fan. So now I want to define, I want to study one cone, how to get the explicit description of this cone. So for this, I want to define a phi here is even a linear map from this Gröbner cone. This is the Gröbner cone, which we call Cn+1. It's just this one we have seen several times, to the tropical flag variety. How this map is defined. So to define this map alpha, I need to use the birational sequence. So if once I have a birational sequence, it is fixed, then I can give all the Pricker coordinates parameterization by a polynomial of big N variables. How I do this? So if I have a Pricker coordinate, so this Pricker coordinate is nothing but some wedge product of some basis vector of the Cn+1. And now I define a polynomial, which is called Fi, to be Pi. This is in the dual space of this wedge product. And this one is the element in U minus we obtained from the birational sequence. We multiply all these root subgroups. And then we act it on the high weight vector, E1 wedge EK. And then this, if I use Pi to pick out the correct weight term here in this part, I will get a polynomial in T1 to Tn. This is the quite standard way. Now I have a polynomial, and I can use some monomial ordering to define a valuation of this polynomial Fi. So if you know the Newton-Alkounkov body theory, what I'm doing is just this Newton-Alkounkov theory, but here I'm quite ad hoc. I don't want to spend time on the general theory. So here I can define a valuation from this homogeneous coordinate ring with respect to the Pricker embedding to n to the n with this lexicographic ordering. Here I always take lexicographic ordering. So I send my Pricker coordinate to the minimal term of this polynomial. It's here is just the minimal term. Here, this is just mathematical writing. I take
you probably need to switch support and minimum, right?
Doesn't really matter. So I just here it depends on how I define support.
Oh, okay.
Yeah. So
No, I think it's correct. What's written is correct.
It depends on how you interpret it.
Yeah, but anyway, it's a technical. It's a yeah. You understand what I mean? I take all the minimal term, minimal monomial appearing in Fi.
So you take the minimal term and you take its support.
Okay. And then I define my map alpha. So map alpha should be a linear map from R to the big N to R to the IN plus 1. R to the IN plus 1 just means I give all the precursor coordinates a degree. So here I choose D, and I need to define what is the degree I give to Pi. And it turns out it's very easy. I just take the valuation and inner product with D, and I take the minus. This is the degree I want to assign to Pi. And this is the most natural degree you can assign to this Pi. It's just an inner product. And here I give one example to quickly let you know what's going on here. So I take S3 to be this very nice sequence, and I computed what is this valuation of Pi here is I, here is this valuation. And now I have this cone C3 is exactly the given by D1 plus D3 is larger than D2, as we have seen. So I take a point 1, 0, 1 in this cone, and I want to look from this procedure, which degree I associate to this precursor coordinates. For example, I look at P2, this precursor coordinate E2 star. It's 0, 0, 1, and I do the inner product of this guy with this guy. I get 1, and I take the minus, I get minus 1. And so on. So I get this degree is 0, minus 1, 0, 0, minus 1, 0. If I look at the precursor ideal, in this case, it's a principal ideal generated by only one element. So this guy will get degree 0. This guy get degree minus 2. This guy get degree 0. If I take the initial term, I will get this 2 degree 0 term, and I get a binomial ideal. And the theorem, I think we proved this joint work with Evgeny, Gislan, and Igor in 2019. But I just give a different interpretation of the different setup to interpret this result. It says the map alpha will send the closure of this open cone to a maximal dimension cone in the tropical flag variety. And if I take a vector in the interior of this cone, the initial ideal is a homogeneous prime binomial ideal. And the combinatorics behind this binomial ideal is this Fegen-Fourier-Littermann-Wimberg polytope.
And actually, in this theorem, in the names of authors, you should have written the last F in Chinese characters, I think.
Thank you.
To make it compatible.
Yes, now I will make it compatible first in color. Yeah, now it is compatible.
Much better now.
Now it's compatible.
Very good. Thank you.
Yeah. Okay. So this is the theorem. I just give a different way to present it. And what is nice of this presentation is that I can not only get our result, but get the result of ego simultaneously in the same framework and same proof. And what ego proved is here in everywhere we choose the lexicographic ordering. If I change this lexicographic ordering to the opposite one, what does opposite mean? It means that if A is larger than B in the lex ordering, then A is smaller than B in the opposite ordering. I take the same sequence and everything is the same, but the ordering is different. And then we will get another maximal cone in the tropical flag variety with the prime binomial initial ideal. This recovers Eagle's work on this Garfunkel degeneration. So, and with this method, we essentially the proof, I can give a slightly different proof combining these two different cases. And the thing we need in the proof is the birational sequence and essential basis, and also Hovansky basis. So we can give a quite combinatorial competitive algebra or this proof to this result. It does not use too many representation theory and Lie theory. Everything is already in this birational sequence setup. Okay, so I hope that in the near future or in the future, I can see more on this thing, because this is essentially a work in progress. And I think now I'm already quite over time, and I would like to thank you very much.
Thank you.
Thank you, Xin.
Yeah.
Thank you.
Being over time is not a problem.
Thank you.
You're welcome.
Okay, thanks a lot. So are there any questions?
Yes, I had a question. So could you go up a little bit? So this even before the theorems, before our theorems. So this construction, I mean, you fixed a decomposition right up there. You fixed it, but this, you could say the same words, obtain a map from the cone for a different decomposition, right? For a different birational sequence.
Yes. Yeah. You can. Yeah.
So you obtain a very large set number of maps.
Yes.
From this cone.
Yes.
To the tropical.
Yes. Yes. So you see this. The point is this definition here I wrote here does not depend. This only depends on the birational sequence and ordering. So, and it works for arbitrary birational sequence here.
Yeah, so you have like lots of cones in the ambient space of the tropical flag variety, but you don't know if.
Yeah, I don't know.
Or do you know any other ones that are good?
No, at this moment, no. This is something I've made. This is some progress I made quite recent. I mean, just 2 or 3 months ago, and it's still in the very beginning of. I try to understand these things. So the nice thing is, but here for the proof, I really need one very particular property of this sequence, which essentially means that I have alpha 1, alpha 1, 2, and alpha 2. This is the thing I need for this proof. Because I can act either with alpha 1, alpha 2, or with alpha 1, 2. But if I go to the other side, alpha 1, 2, alpha 1, then I can't always act on this E1 minus E2. See, this is not a very good example. Maybe I have to write here. I have to write alpha 2, alpha 2, 3, alpha 3, something like this, or alpha 2, alpha 2, 3, alpha 3. So you see here, if I can act by alpha 2, 3, then I can act by alpha 2, alpha 3.
Okay.
In most of the cases. So if I change it to this sequence, then I can act by alpha 2, alpha 3, but alpha 3 is to the right of alpha 2, because I always act my birational sequence from right. You see here, from right. So this would be another property I need for this proof. The other thing is just not only convexity, but convexity with the correct order.
Yeah.
And the other thing are just the Minkowski property, and that's only thing I think.
Okay.
And then
Got the question? So I have one. You mentioned Quiver Grassmannians on the first slide. So how do you enter the whole story?
Okay, so let me go back a bit. Yes, I wrote there. Sorry, I forgot to delete it because it's okay. I thought
noticed.
Yeah. Okay, because that's something I had in mind as an example, but you see in this degeneration pole set, essentially it can be mapped into, I just write in red. So this guy can be mapped into some cone in the chop flag. And now I want to understand what are the facets, what are the varieties corresponding to the facet of this cone we studied. And now, if there are two kinds of inequalities, these are the 3 terms and the 4 terms. And if we take some of these varieties coming from facets of the tropical flag variety are isomorphic to Quillgrass manias. This, I think, is what I plan to state. This is essentially in our joint work with Giovanni, Ghislain, and Marcos, but just in a different language. Sometimes this degeneration given by the tropical flag variety is really degenerating the inclusion condition.
I see. I see.
Yeah, that's kind of what I was asking at this point, if there's like some more down-to-earth interpretation of these intermediates.
Okay. Yeah, some of these intermediate can be
Linear
done just degenerating the inclusion.
Yeah.
These are the Quillgrass mania.
That's what you call linear degenerations, right?
Yeah, this is called linear degenerates. Yeah, I think this example you can find in the in my paper with Misha.
Okay.
Okay, thank you very much. Further questions? So if not, thank you very much again for the fantastic talk. And actually,
thank you.
Thank you.
Yeah. Thank you for
it was very nice meeting you, at least in this regime. So all of you and Peter, Bea, and Xin. So thank you very much. And well, yeah, see each other sometime.
Yeah, I'm looking forward to meeting you either online or offline in the future.
Yeah, me too.
Us as well, yeah.
Yeah. Thank you very much.
Thank you.
You're welcome. So Igor, let's keep in touch. Yeah.
Yes, I will.
Yeah. Okay. See you.
See you. Goodbye.
Bye.